Okay, so this is to import the data. This is to display the first few observations, actually 6 rows. And then you can use tail as well, which will be the last 6 rows as well. Okay. So when we do it like this, okay. But now this is now a data frame. So for example, you can check, let's say the structure of wind. If we check the structure of wind, this will be a data frame. But because it's just one, it's a data frame with just one column. So I can as well use it as what a vector. Is that okay? Yeah, so we can collapse it. If you want to do that, you can just wind, and then you can just use on list. So even though it's a data frame, if we do on list, it will then be a vector. So when we come here, I should have deleted all this. What's the name? Is wind, right? Oh, how come I'm not? Let's see. Yeah, so wind. Okay, on list. It names it. What do I? Okay, so let's see. Plot. It's still a vector, but let me just cross check. The margin is too small. Yeah, so the data set is like this. So yes, we have a vector of this. Okay, and the first question was that you should obtain descriptive statistics. So let's say if you get this data and you want to work on it, you first start with descriptive. What is the data? So for example, I plotted it, it looks like this. Maybe I need to check the margins just so it's okay. Yeah, so wind and then index. Okay, so basically, I mean, if you look at this, we have about 3,000 there, about, or maybe more. Yeah, okay. So that's it. But I can get a summary statistics and see how this wind speed looks like. So the minimum is 0.925, the maximum is 6.4, mean, and so forth. Okay, you can also use box plot. So that's graphical. Do you remember that yes, with this you can describe what the shape of the distribution is. Okay, of course we can also get it from here, from the summary. Remember that you also install the package psych, right? So you can use that to even get even more descriptive statistics by using what? Describe. Is that okay? Now, if you get this, you cannot just write it. So the variant, here we get the skewness, kurtosis, and so forth, standard error. Some of them are repeated. But when we look at it ourselves, we should be able to describe it from this graph. So what can you say from this? If you were to get a box plot like this. What can you say if you have to describe this? There are some outliers. Yes, but how would you describe this data? You can't just say there are outliers. That's just one observation. What can you say? You know, when you have graphs, you need to tell a story. So you start from somewhere. And so for you have all these restrictive statistics. The number of observation is 2,780. And you see that from here, so the index is just numbering them 1, 2, 3 up to that number. So you see it over here as well. The mean 2.64, right? Here we had 3 decimal places. The other one is 2 decimal places. So basically they say the standard deviation is the median is that. So what can you say about this data? Yes, so we have only one observation now, that there are outliers. And even that you can do more, you can say more, not just outliers. The data is all. What does that mean?
That means most of the values fall in the lower range.
What is lower range?
I mean, there were more.
What will help you? What graph will help you to say what you are doing, or what you want to say now? Good, yeah. So you can also plot the histogram of wind, and it looks like this. So, as I said, there's no need to do this. You need to take out the. So actually, the S lab should be what? Wind speed, right? Actually, average wind speed. And this is in, I think, m per second or something. Something like that. Okay, so average wind speed like this. Okay, so now what can you say? So we have all this plus the descriptives. What can you say about this? Yes. It's about. It's about 600. Are you more interested in the frequencies? So the frequencies, you must relate it to something. What are you discussing? Or what data is available to you? Wind speed, yeah. So the frequency of the wind speed, maybe, yes. So you look at the class with the highest frequency. So most of the wind speed were between what? 2 to about 2.5. Is that okay? If you look at this, this is it. So that's one observation, right? Okay. Most of them were within that. Or if you like, you can put, yeah, so the mode, this is actually the modal class, right? Okay. And then the least, there's some, you see some here as well. So the least is a bit difficult. But at the extreme ends, you have those smaller frequencies. So that's one. What else? And only a few of the larger wind speeds, yeah. Outliers actually. We don't have any outlier at the lower end. But remember that this also has very small frequency. So if it is small frequency, then it's like it's rare. But its proximity to the other values will determine whether it is an outlier or not. So in this case, it's quite close to the other value. So that's why when you come to the box plot, you don't see any outlier at the bottom part. Now, what about the mean and the median? So the mean is what? Larger than the median. What accounts for that? The skewness. In what way? Yeah, so you have some observations that occur over here that are larger. So they tend to pull the mean towards that end. That's why the median will be at the left side of what the mean. Okay, so I mean but you are not going to take the graph and then you say, well, less than 1 we have this. Between 1 and 1.5 we have about 400. Then we say you are walking through the data. Okay, you find some descriptives, like you have a table, the frequencies are in the table, then you are now you are walking through the data. So get your graph, but get the most salient points from the graph and interpret it, right? That the mean is greater than the median, which signifies that there are more larger values than smaller values. Okay, but this is used advisably. If I say more, it means they are rare, right? You know, when you look over here, they occur less frequently. So if they occur less frequently, then it means they would distort the data. Okay, so yeah, okay. But that's what you are seeing in the skewness. But the skewness is not that large. It's just 0.84. Okay, and so forth. And ketosis 0.72. So this data is not really heavily tailed. Okay, all right. So that could be enough for your first part. Of course, we've done both graphical and numerical, and this we don't restrict you. So it's up to you to decide what form of graphical display you want to, to tell your story. Okay. Then the next one, you were to write a likelihood function in R for the above survival function. Okay. What did you do? Remember, we talked about 2 ways of doing this, right? What is the first one? Yeah, we can look at the survival function because we were given the survival function over here and obtain our likelihood. How do we do that? You find the product of which one? This function. Which function are you talking about? The survival function. Okay, how are you going to do that? You have to differentiate, yeah. So what you are saying is a PDF, but this is survival. So if you want to do this, you need to find the differential. Negative of the differential will give you the survival function. Yeah. So, sorry, we'll give you the PDF. Okay. So we can differentiate this function. Negative of the differential of that function will give us what? The PDF, and then we do so. But R also can do that differentiation for you. I think it's D or something. So you can type differentiation in R. So there's a function. Yeah, you can differentiate. So the big D function is for differentiation. Okay? So I can write my function, which is the survivor, pass that function to D. So look over here. So if you have this expression, you can see. It went off. Because of the, okay. So I just type differentiation in you can check Google and you'll get something like this. So you write the function as an expression, then you pass it through the D function, which is differentiation, capital D. Like this. So what I need to do is to write F as, let's say, expression. So in this case, it's even S, right? I can, because this is my survivor, right? The survivor function is what? Is equal to E. So ESP negative X over what? S, right, alpha, like this. So this is my survival function. But in R, if I want to do this, I need to write it as expression. So you have expression. So expression is actually a function like that. And then S will be equal to that. Now, if I pass this S through this, then it's going to differentiate it with respect to X. I think you need to even do to X. Let me show you. Okay, so like this. So this is like an expression F with respect to X, right? With respect to X. Not just one like that. So this will differentiate this. So remember that when we're doing the optimization, you realize it has a gradient. The gradient will be the differential. So if you want to put, you can do so and then R. But if you don't do it, it does it automatically. But as I said, later on when you are doing simulations and so forth, and it's quite large, you need to help R do some of these things. And in that case, you have to be differentiating. So you can actually differentiate it in R, get it, and then now you put it in as your gradient so that it will speed up the process of differentiation. So you can, I just type like this, differentiation in R, and you have so many of it. You can do integration as well. So we can use R to do all these things. It's up to you to explore some of this stuff. And you can evaluate it and so forth. Okay. All right. So that's one. So you can do so by differentiating and so forth. But we know that we have also some weighable distribution in R, right? Yeah. So, but it's dicey. When you want to do this, you need to check whether your function is written in the same form as what is in R. If you remember the gamma, there are different ways. Some will write the scale as 1 over beta, right? So, yeah, so you need to check and so forth. So the B part, section B, we said you can, so let me make a comment that you may differentiate. You may differentiate x of x, right? To obtain, so that's I. One way of doing it is that you may differentiate s of x to obtain f of x, right? And that is equal to negative d dx of what? The survival function. Is everybody okay? Once we do that. So in R, we could have done so if we, from what I have shown you, if we have our x as expression, to be expression, and then you put all this in ESP and so forth, then you fill it up, and then you find the D. Remember, that will just be your D of F, right, and so forth. But it's easy for us to use what is in the inbuilt. So through inbuilt function, inbuilt weighable function. So the other way is to use the inbuilt weighable function. So to do that, we do R weighable, and then we check. So when we come here, this is the PDF. So actually when you, but we know the survival function. So you see this, is it the same as what we have in the question? It's the same. Okay. Because you need to send one to the other side. Then it becomes the same as what we have in the question. This is it, right? So if I send F to the other side, it means this will go to the other side. Then we have exactly what we have over here. Okay, so what do? It's the same. It means that we can get the densities from here. Please, are you okay? Yeah, so we can use D weighable, because the D weighable is the density of the weighable distribution. So we can use this. We will pass our data in there, and then we use that one to find our our likelihood function. So, so we can talk about negative log-like function will be a function that will take the data, if you want, you will say data, and then some power values, right? Parameter or theta naught. You can expect theta 0. So which is that it takes theta at 0. So now what do we do? So our LL, our log likelihood, will be what? You said negative. Remember, when you have the F, you find your log likelihood of theta as x will then be on the product, right, of f of x at theta, right? And so, but then we find a log, right? But remember, now we find a log, it becomes L theta x. So that is what the sum of what log f of x, right? But we want negative of it. So this f is what we are saying is d-weighable, right? So d-weighable, then we take negative of it. So that's what we are doing. Okay. So, or maybe I do this and then we sum. So it's sum. Okay. Then I put in my d-weighable. Okay. What is x? X is going to be the data. Then the shape may be theta, so it means theta will be what? A vector. So the shape will be theta 1, theta naught 1. Then what about the scale? It will be theta naught 2. Is that okay? Yeah. Log is false, we can leave it out. Like that. So that's our log likelihood. No, we need to sum log rather. Sorry. I need to find the log of this. Log of that is sum log. Okay. Then I can now return what? The negative of the likelihood. Is that okay? Then we get a negative of the likelihood. Remember, if you don't do this, you won't be able to find the maximum. We want the maximum, but this function, the optimization function will find the minimum. So we negate it so that the minimum now becomes the maximum. Okay, so that's it. So this is quite easier than differentiating, but that is if you have the function in R, okay, which we have. Okay, so we can resort to this. What else do we have to do? Then now we can do our optim function, right? Okay. So, yes.
You set your log as true instead of putting the log into bracket.
It will find the log of the data. Yes.
And is that that's weird.
Yeah, but okay. So you can come here and check what they mean by finding the log. So log P, logical, if probabilities P are given as log P. Well, here, yes, if you, so by default it is false, right? And we haven't given any probability in terms of logs, yeah. So it's better you leave it as a default. So I could have left it. If I take it off, it will still take the default values, yeah. Remember that you see, in some cases, if I have a data set, I may not repeat them. Okay, so I can have a data set. Let's say I collect your ages. Some may have the same age. When I want to pass that data into a function. Instead of repeating the age, I can just use one of them and rather attach a probability to it. Yeah, because the probability of it occurring will be the number that is in the sample divided by the total number. So that makes it, reduces the length of the data you have to key in. Yeah. But we are not interested in that. And always remember to put your name, the name of your functions in that. Okay. So the next thing is that, can we get this in an optimization routine? Yes. Okay. So general purpose, we copy and filling, right? Okay. So the parameter, maybe we start. You have to know what are the you need to go to the distribution and check these parameters. What are their domains? So the shape, can it be negative? Can it be positive? So you come here, it will show you. Okay, so we are not giving. Yeah, but the shape of a Weibo distribution, the EVI should be negative. Yeah, so let's see. For the scale, it should be greater than 0. The shape, let's see. If I have this as positive, if it is negative, I'll have okay, so let's just pick 1. Yeah, so we'll pick, let's say 1, 1, just to be on the safer side. Okay, then the function that we want to minimize is what? Is negative log, like. The gradient, we can take it off. We don't need it. The method, the default one is near the mid, so I'll leave it like that. But it means that I will not need the upper end and lower limit. Okay. The Haitian, I may want true, so I try it, of course, and then I don't need to take out. Remember that what is our data? Our data is equal to wind, right? So usually, you see this function, what you put here must also come within the obtain function. Other than the obtain function will not have any data set to work with. So because I use data, I must keep in that is data, but that data is equal to wind, right? Are you okay? Yeah, and it must correspond. If I put data here, and this one is capital D, it won't work. I can run it, we'll see. Okay, so you see, first of all, I haven't even done this, right? Okay, so I'll do it again. Okay, so you see, I'm not really getting anything. Error in, you see, data. Even though the wind is there, it is not recognizing it within that function. So we go there and change it. Which one? That, so it gets you the matrix, which you can get your standard errors of the estimators from. So the Haitian matrix, you can use it to get your standard errors. Yeah.
And so please, why did you turn the wind data into a vector? Couldn't you have just used it whilst it was in the data?
Yeah, we could. Yeah, I made mention of it. That we can read the entire data and then we take out. Yes, yeah. Yeah, it can be a data frame, but it means when I'm calling, I need to put the dollar sign. Yeah, and then it becomes a vector. So I've now changed the data, and then I'm going to try it again. There. So you see, we now have our estimator. Let's see how. So these are the parameters. The shape is 2.79. The scale is what? 2.96. Okay. So maybe if this is the Nelda mid, right? I can also take that out and leave sun. So depending on what routine you use, you may get different results, right? But sometimes they are.
Would you allow for the disparities in results during the exams?
The
The disparities in the results during the exams?
oh
They are just marking them.
no. But I mean it's so even the marking scheme is just some guidelines to mark because I don't expect that all of you will write the same thing. So I leave it open. I said descriptive statistics. So I'm looking at what you and whether what you are using sounds convincing, and then I mark it. So I don't expect everybody to use a histogram, but if you use a histogram, have you labeled it correctly? Is there a title there, and then you have also given? Those are some of the things I would look at.
So please, why did you use this method?
Yeah, so I'm even trying. It's because each of them has its own how should I put it? Strength and weaknesses. Yeah, so you see this, it takes a long time, but it's quite a good method. Yeah, but it's simulation, so it takes a bit of time. Unlike the Nelda mid,
So we are not restricted to any.
no. That's what I'm saying, that as you go on, maybe when you get, sometimes it doesn't, some of the methods will not work. And some require constraints. So if I want to use the LB, these ones, yes, those ones, you need to now provide lower bound and so forth. Yeah, so, yeah, but it's not that different. 2.76 is, if I go back to the other one, we got 2.76722, right? And I think it's basically the same. Something, yeah, so, and then the value, the function, the value of the function, which will help you to get your AIC, BICs, are also given. The Haitian will help us to get, so this is the variance for the shape parameter. This is also the variance for the other one. And then we have the covariance between them. And we can take this to get the facial information, and then we can get our standard there. Okay.
So is any reason why they interchange the position of the variances?
No, because this one is it's what do you call it? A symmetric form, so we can actually leave half of the matrix out. Because what you have on the upper part will be the same as what you have on the lower part. And the diagonals are variances. Yeah, so the up diagonals are covariant. So the covariance of x and y is the same as the covariance of y and x. Yeah, so you should get the same thing. Okay. So that's it for the optimization. If you want just the parameters, you just put pi here. So in this case, if I do it, you realize, and you can also, or maybe the easiest way is that you put it in a fit. So MLE fit, or or maybe theta hat, not theta. Okay, so MLE fit will be this. Okay, so we do that. It takes a bit of time. So you can imagine if you are doing this over and over and over again, yeah, it can take time. So, and it gives you a warning that there were some, of course, it's simulation, so you don't expect all of them. So there it is. So the same thing that we got, okay. But now, because I have done that, if I want the parameters, all I need to do is to put then you have all those, the H, and so the parameters are that, and so forth. So it's easier now to use it. So that's is it B and C? Yeah, that's B and C. Yeah, so we've done so. Is that okay? Then we are required to get some insight on exceedance probability rate in so and so and so. So determine the probability that the average wind speed exceeds 6 meters per second. Compare it with the. So basically, what you need to do is that the empirical one, we have to check how many of these wind speeds are greater than 6. Is that okay? So what can I do? I can go to this is so this place. This is D, right, or C? Okay. A, B. B is the likelihood. So C is the fit of and this will be D. Okay. So D, so the empirical exceedance. In other words, how many of how many of the wind speeds are greater than 6? So what can I do? I can just do this. Wind greater than 6. Okay. But this will display true or false over 2,700 times, right? Okay. So if I go up here, you see false, true, and so forth, right? Okay. So what I can do is that I can also just take. Okay, if I put wind here, what do you think will happen? What will happen? I hope you have submitted your work. Have you submitted it? Are you sure? No, but when I started, it wasn't written. So if you are giving me what I'm doing.
Oh, no.
Okay, what will happen? If I run this code, what do you expect? What number? It's called try. Okay. Yes. So the inner one gave me true or false. Now if I pass it through the vector, what will happen? No, we did good. This is subsetting or subscripting. So it will only take those that are all true. Okay. So here I'll get all you see all of them are greater than what? 6. See the values. They are all greater than 6. So it means that if I also if I want to get the exceedance probability, there are several ways to do this. I can get the length of wind and divide by the number greater than 6. Greater than 6, right? Okay. Alternatively, I can take this and find the sum will give me how many? Okay, so sum of this, true is 1, false is 0. So if I do this, I'm going to get 17. Are you okay with this? Okay, good. So if I talk about mean of this, it's going to take the whole wind, how many of them, the sum divided by, that's what the mean is. Yeah, so that's the exceedance probability.
So is this also another descriptive way of describing the data?
Yeah, so what we are doing here is this. Okay, so let me go back to the plot. Okay, so you have this, assuming, so the idea is that you are an insurance company. You want to give insurance, is it, what do you call it? Is it household insurance or? Yeah, building. Yeah, you want to insure buildings, right? Property insurance. Now, you have wind speed data. You are insuring them against wind and so forth, right? And you have wind speed data. And this is the data. Now, you have to predict how many times you can get wind speed above this. Because maybe when it is above that, it may result in damages. So if you know that and it is rare, then it will have effect on your premium. If it occurs frequently, then you need to also up your premium. So that's what we are trying to do. Because some of this analysis will aid into your decision on premiums. So this is about when the next time it can be something else. Yeah. But the earthquake and so forth. If you take earthquake data, you need to know that, well, when the Richter scale is, let's say it is above 6, what happens? Okay, then you can use that too. So if in Ghana we haven't experienced that, and you are insuring, somebody they want to insure above that, then you say, well, maybe within the year it won't happen. So you can afford to lower your premium. That's how you do some of these things. So that's why we are doing such exercises. Okay, so this is my empirical exceedance probability, which is P, let me call it P naught. P naught hat. So this is what the data is telling us. Okay. Now, I can let you fit a normal distribution. Is that I think that's what I did. Yes. So I said now fit a normal density. Okay, no, that's okay. So I had wanted to do that. Maybe I should have added it as F. That you can fit a normal density, Weibull density, even other distributions, right? When you do so, you can check which of them actually fits the data well, of course, with pictorial view, right? But, pardon me?
That's what you said.
No, but the next thing is to check which one fits the tail well. Because you may have a distribution, that's the one I did not add. You may have a distribution that will fit the central part of the data well, but you are interested in the, the extreme part of the data.
Yeah, so the one we did there.
Yes.
You realize that
Yes.
the earlier part of the data, like the central and then
Yes.
the left side,
Yes.
you realize it was very okay, but when you go to the extreme,
Good.
you're
Yeah.
able to superimpose over the top of the bar.
Yeah, the mass. Yeah. Yeah. It means it is underestimating the frequencies. Yeah. So I mean that's my research area, like statistics of extreme. So at the central part you can get any distribution to give you very good estimates. But it is when you are going to the rare part, and the rare part may be very large values. In some cases you are talking about very low values. Okay. So that the bit part I did not add. Okay. So what do we do here? Well, so we can now estimate this same thing, which means we want the survival, right? We want the survival function at x is equal to 6. Okay, but we have already estimated our values for the scale and what? The shape. So all we need to do is to find the survival probability. How do we find the survival probability?
1 minus fx.
1 minus fs. What is your f here? You use what?
It looks like a like
So you use a function to get it. Okay, so which you can do so anyway. You can write the function for the survivor and put in when x is equal to 6, and then the shape is what you got from your. But you can also, because we use the D, we can also use the P. Remember the P if you come here. So don't forget all those. P is what? It's F actually. Do you remember this? P. Yeah, so the P variable will give you what? The distribution function, which is your F. Okay. But it also has lower tail is true. So if I set the lower tail to be false, it means it is the upper part. It becomes my survivor function. Yeah, so two ways, but this is easy than going to. So you can do it here. That let's say P1 hat, which is what you actually got. So the Q will be 6. That's the quantum. It's like if I go here, the plot, okay, just a moment. What I want to do is to find V is equal to 6, color is equal to 2, line weight 2. Okay, so this is what we want to find. Okay, we want to find what is the proportion of wind speed greater than 6. Is that okay? Yeah. Okay. So now here we put in what is the quanta. The quanta level is 6. Remember the quantas are your wind speed, right? Then the shape then we go back to what was our MLE parameter 1. So the shape will be this 1. What about the scale? 2. Good. And then lastly, is it the lower tail we want? No. So we want the upper tail. So we put this as a false. Log P, we can just leave it like that. Okay. So if we run this, we will get this. So remember the P hat from the data. Oh, I did not do this. The data itself is 0 point. What is this one giving us? So what it is actually underestimating the probability. Okay. Now if we fit the normal distribution, we can do the same exercise. So in an examination I can tell you to find which data fits the tail distribution well. Okay, and even the tail I can give you maybe 5, 6, 6.5 and so forth. This data doesn't have a longer tail. But if it has a longer tail, there's this data called the Norwegian fire insurance data. It's a very widely used data in insurance. Yes.
Why was there a spread between both values? The P naught hat and then the P1
Yes,
hat?
because this is the actual one. P naught is what really is happening in the data. But you have fit a distribution. How well does the distribution fit this data? So if you look at the frequency, it is actually underestimating it. Okay, so if you are using this to make a decision, okay, you will say that it's almost, we can take the percentage of it. Okay, it is rare if you are using your distribution, but the data at times says that this can even occur quite often. Okay, so here there is a 0.6% chance that you will record a wind speed greater than 6. Your distribution is telling you that there is 0.08%. Do you get what is happening? That's it. So the idea is that you need to now expand and check whether you can have other distributions that will fit the tails quite well. Okay, so maybe, I mean, as an exercise, we can check whether we can fit a log normal or any other thing. So fit, maybe I should leave it to you as an exercise when you go home. No, we need package mass, right? Mass. And then there's fit this R. Remember, we have several distributions in there. Okay, so let's see. We can use a log normal, right? So let's just fit it, and then we see how well that fits the tail. And then we fit the normal as well. So you can now have, so L normal, L norm. So log normal. So X is still our wind data. The density is log normal. We have two in there. I haven't really checked which was the difference between them, unless we go through the codes. Okay, so here, so the mean is this, the standard deviation is that. Okay, now I can now find R, it was RL norm, right? Yes, good. Hello, dog. Yes. Evening, yes. How are you? Okay, good. Yeah. I was supposed to call you. There was another paper that I put in. Just keep it for me. Yes, yeah. I was going to call your husband to go and collect it, but I think I forgot again. So just keep it because they are here to write it. Okay, all right. Monday, all right, okay. Thank you. Yeah, that's fine. Yeah. Okay, all right. Thank you. Okay, so what is happening is that now we can also come here and take P norm, right? PL norm. Okay, so we just fit in what, so L norm, so let's say P2 hat is for the log normal distribution. So K is still 6. Mean will be this. Estimate 1. Okay, then let me bring this one down. What about the SD log? That will be this estimate or 2. And then what else? Lower tail is false. Log P, we can leave it like that. Okay. So let's see. P2, 0.09. Okay. So now I can put them together. It was what? C, the first one was what? P not hat, P1 hat. Of course, we want the one that will give us the best. This is P1. So when we get a normal distribution, we can also add which one is closer to 0.06. Of course, this one, right? So the log normal is giving us something closer. I can do the same exercise with normal distribution, and then I check. So that's how you evaluate some of this. But you realize that if we check a quantile level, maybe at the middle, the performance will be different. And that's what you see in your the fit that you did, the superimposition. Yeah. Okay. So I think the rest you can continue, right? So please add normal distribution. Which one again? Gamma. What again? We've done, was it Weibo part of this? Weibo, yeah. So it means you have normal, Weibo, log, normal itself, gamma, what else? What? Pareto, okay. So add Pareto, and so far you can try any other one. But when you finish, get it in a data frame, right? So you have your empirical one at the top, and then the rest at the. One other way to check it is that you can use the empirical as standard when you are doing your thesis. Use the empirical as standard, and then you compare each of them to it. You can express the value as percentage of the standard. Okay, so if it is equal, you will get 1. Okay, so if, let's say, I divide each of them by the standard, then I expect to get 1. If I get a value greater than 1, it means it is underestimating it. If I get a value less than 1, it means it is what? Overestimating it. So that's another way to do it. Okay, but I mean, it's up to you how you want to do it. That's more or less like a relative performance of them. Okay. I think that should be it. The other one we did some, so you should be able to do it. The only clue is that when you are doing your histogram, you must make sure that it is not the frequency.
Yeah, frequency is false.
Yeah, the frequency will be false.
I see.
And then also, I think the arrangement, you need to sort the data, right? Yeah, you need to sort the data. So the E, let me just put the comments there. So 1, what do you need to do? The normal, you need to estimate it like we have done.
Yeah.
Is that okay? So, and you can actually put all the distributions we are talking about on the actual data and give a legend. Yeah. And so forth. So please try and do it and bring it next week. So, what do you do? What we are talking about. All the other distributions. So, E, you have to superimpose the densities. Okay. So how do you do it? Well, you need to. Okay. So first of all, I'm just giving you what you have to follow. Histogram. So draw your histogram with relative what? Frequency. So it must come with a relative frequency, right? Okay. Then for each distribution, you need to find the density, which means you use the D norm, D Weibo, D that, and so forth. So each of the D, you pass your data through it. It will what? Give you the density. But you see, the data is not arranged in order, so it is easy for you to start first by arranging your data. Then you get all the density. Then each plot become easy. Is that okay? Other than that, it will give you. We demonstrated this in class. Yes. So it will just be. You get a shape, but it will be haphazard. Good. Yeah. So just make sure that. So let me give you this. So sort the data, the wind data, right? The wind data. Then calculate. So this is like an algorithm. When you write your thesis and you do simulation, you need to, it must be reproducible. Okay? So when you are, like when you were doing your paper review, if they have done simulation and they haven't demonstrated how it was done, that's a criticism. Because then it will be difficult for somebody to reproduce. So the paper that I gave you, you realize that they will tell you that simulate this, do this, that, and so forth. Just that they may not add the code, and then you need to sit down and do it, but it should be fine. So you calculate the densities using D. I'm putting D because you may have different example. So let me say example. Oh, what's this? Example like D norm, right? So the D norm, you need to put in that data that you have sorted, and then it will give you all the densities. Okay. Then what do you do next? If you get a density, what do you do next? So it means the data, because you sorted it, the x-axis is also sorted, right? So you take your sorted data and its density and you lines it on the graph. Okay. So take the sort the wind data. I don't need to provide because everybody will have a different name. But sometimes, I mean, if I'm doing it, I'll either put S there, or let's say sort dot wind, something like that, just to show that and name it. But I don't want everybody to name your data sort dot wind. Do you get what I'm saying?
Yeah. That's the name I use there.
That's it.
So even if it's true, like that's what I did.
Okay, all right, yeah, but you need to differentiate it from what the actual data. So you may put maybe S underscore win, something like that, okay, to distinguish it. Okay, then you take the
The sorted data, is it supposed to be in any, increasing or decreasing order?
you can do it anyhow, but I mean increasing order is fine. Yeah. Okay.
The default is increasing order.
Yes, yeah. So just use the default. So take S wind and take X wind and the probability, the densities, and superimpose it. Superimpose. So you superimpose it on the histogram. Actually, relative. If you don't do it, relative histogram of wind data, what will happen? All of them will be at the bottom part because the density is what? Between 0 and 1, where the frequency too was somewhere even over 600. Is that okay? Yeah, so this is what I mean. This should be converted to what? Density or relative frequency. So that's it. And that's it, of course. And then provide legend, right?
Yes, sir.
Provide legend. Okay, so nicely. So this, if you want to put your legend should be on the top right.
Yeah.
Because there you have enough space. Don't come and put your legends here, then it will distort your graph. So, and it's okay. So it depends on what your graph is, and then you decide where to put it. That's all. So please go through this, and I think it will be enough. And I sent this introduction to life insurance. You just did this. Please go through it. So if you look at it, this is a paper. I give it to you every year. I give it to the people. It's a paper, okay. The so it's about the package life insurance. Okay, so please, you are still doing life insurance. So please compare the things that you are doing. You can do it over here. So if you take it, first there are life tables here, right? And this will help you as well in your project. Is that okay? So if you want to do something on life contingencies, you have a package that will help you to do it as well. Okay. There are others associated with this. So TPX is this, TQX, TDX, TLX, expected number of years lived by a cohort, TMX, the central mortality rate, and so you can, and then here the curtailed expectation of life, and so forth. You can compute all this in quite easily. Okay, but you should. I mean, I am not going to test you like you have over here, right? Because then it's like the course is like life contingency. Okay, so I'll just check the basis, and the basis are that if I give you like a formula, let's say category expectation, can you actually write a function to compute the category expectation? That's the computing aspect. Okay, but I mean, let's say if I'm teaching you this in conjunction with this one, then I'll write over here that do those things.
That's how the courses are supposed to be. You be right from the
So
200.
yeah, so at the point, what I wanted to do, it still doesn't work. But I mean, I wanted to run this course before you even come to take the course. But that was how I was trained. Okay, so 2 weeks intensive, you have to come 8 to 5. Will you leave your work and come 2 weeks? So those were the challenges. But ideally, if we take 2 weeks, you should be able to go through this. And because it is constant and you are doing it every day, by 2 weeks you are okay. Okay, then maybe we meet during the semester and so forth. But it means that everybody will have to also let you do assignment in this.
Yeah, like, I was
Yes.
even trying to see that
Mm.
undergrad, you're trained to this for 4 years, and that's level 400, you have to do art, and I come to do all the things. Like,
No,
right?
now we do it twice. At level 200, then we introduce you to it. Yeah.
So that, like, the courses that you're doing, you're applying to.
Yeah, then you apply small.
By level
So,
400.
yeah, then you are okay. Yeah.
That's
So
fine.
that's how we've done it. Yeah, we've moved from somewhere when there was nothing at all to now. Yeah, so we will get there. Yeah, but that's another way around it. I prefer it, but the implementation is a bit difficult to get people, because when you mix it, then it means it becomes a problem as well. You can't afford to mix a day. Yeah, but it was helpful when I did it. Yeah, it's true.
Insurance companies, do they use app?
Yeah, some do. I've had some who requested for national service people, but they stated specifically the person should be proficient in her.
Yes.
Yeah.
So is there any other software to use apart from?
Oh, there are. That's all. Even Excel. Excel does so much. But I mean, we can't be teaching you Excel here. So yesterday we had a meeting. I was asking whether the student was in this department, because I told them when I start this that, well, if you can do this, then Excel should be very easy. Yeah, because I mean the things are there. All you have to do, because most of these things we are doing, you can do it in Excel. Yeah. Just that, when you want graphs and other things to Excel graph is not that, and so forth. And you want to implement a simulation study in Excel, you need to program as well. Because nobody knows what you are doing to do it that way. If the thing is a common problem, it will be implemented in Excel with a function, right? But if it is not there, you can also combine some of the functions and get what we are doing now. But it's easier when you do it in R. Yeah. Some also use SAS. Yeah, SAS as well. You can learn about it. There are student versions and so forth. Some even Python. Yeah. So please do. I mean, at this level, you can't be not proficient in this. Yeah, at least one, and then a fair knowledge in the others. So you take maybe some 1 week, then SAS. You get an introduction to SAS, introduction to Python. It's almost the same, the same. They are all object oriented, so they are around the same. Just that the sentences are different. So when the opportunity comes, it's on your CV that you are proficient in this. Then you go to the interview. They say yes, you will learn, because you have some of this. When you go and there's a problem, the internet is there. It's not like exams. Yeah, but of course you can't do everything on the internet. But you have the background. So when they give you a problem, you have internet to help you as well to do it. So that's how you should approach it. What were the difficulties? How to form a function?
Function building.
Okay, so I gave what is it? The structure. Okay, so I can. Yes, those who. Yes, I think we are done now, but I will stay for questions if you have any.
Okay, so quick question.
Yes.
Say, look at something, please. Before we change the topic.
Yes.
This is the work that we did. Right?
Yeah.
This is what we did.
Yes.
But if
So
you want to comment on the.
If you want to comment, so you see, the blue one, the Weibo is actually underestimating this one.
But from here, it looks like the Weibo is performing.
Yes. So if you look at this one, the Weibo will fit the lower tail better than that one. Do you get it? Because it is closer to this. But here it is underestimating that one. Just that over here, they are almost the same. Okay, just that this one is at the middle. And when you come here, this is up here, so the normal is better over there. And then when you are coming here, the normal is blue. The tails is still better. But in some cases, it does well. It does better here than that one, and so forth. Yeah.
So, but we did a mistake, a very big mistake in our work. Not like, I guess when you came, we were like,
Yeah.
sometimes out.
Yeah.
So, like, we just did plagiarize it. But later I realized that the time was, we realized the time was extended.
Yeah.
So, we submitted our actual work. So, when you even look at the codes, you know that it is not AI, it's like, what we're teaching us, like, correct codes compared to the one we submitted AI. You immediately say it's AI. But this one, you realize, like, what
So you did it, yeah.
so like you see it's obvious, so that one yeah. So we resubmitted it again using another member's ID and then we stated on it.
Alright.
So when you see that, you check this the correct check for our group.
Okay. So please print it and bring it, okay? Can you print it just there and bring it so that I can mark and give it to you next week?
Okay. So
Okay.
the new one with the multiple.
Yes, you have two
With the multiple
assignments to give me now.
Yes.
Printed one.
The hard copy.
Yes. Yes. Next week. Oh, I wanted to mark. Then you see your mistakes before you've seen it. Oh, they are there. Oh, over here. They are not there.
Everybody's not submitting.
All of them.
Yeah.
Are you sure?
I checked.
Where did you print this one?
Yesterday.
Yesterday.
Yes, because the weekend they are not here, so
Okay.
probably next week.
All right. It's today Sunday.
Saturday.
Saturday. Ah, they used to be here. Okay.
Thank you.
All right. Or during the week if you can.
If okay.
Okay.
Okay,
So
then I
that's
will
how.
say then during the week we pass by.
All right. So you have the name. You have the name, the keyword, function, arguments. It will be part of the video as well because I'm recording. Yes, so I'll post it. You have access to it. So yes.
These are our comments.
All right. Okay, so you have the body of the function. How is it going now? Then return. Are you getting? And then what are you? You want to take?
Yeah, the paper was, I had a here.
Okay. And then return what? Return your answer, so to speak, or results, I should say. So this is the structure. So it needs a name, the keyword function, then the arguments you put in. Then you write some body of the function and then result. Is that okay? All right, okay. So I'm going to do an example. So a function to compute what can I? Let's take something like, let's say, BMI. BMI of a person, body mass index. Okay. So we will call the function BMI. BMI. So the BMI should be a function. What do you need to calculate your BMI? Height and then weight. Is that okay? If we get this, we should be able to compute the function. Okay, so I open the bracket and the bracket, right? Okay. Now, so you can go online and check. Yeah, because it must be within it to that's the structure. So it must be within the curly bracket, so that when it takes the name, it runs through what is in there. So that's it. So BMI. So yes, it's weight over height squared, but it should be in meters. So we can compute the BMI as weight divided by height squared. So it means that whatever you are putting in must be in kilograms and also height. Oh, sorry, and meters. Okay. Now, so I can return BMI. Okay. So this is a simple function which I have run it now. So now, if I get the weight and height of some people, I can, so the arguments, so height, let's say the person's height is 1.70 meters. Weight is 80 kilograms. So the BMI is 27.68. Okay, so I can go online and height, this is in feet. So this is the structure. So it's the name, the function, these are the arguments. This is the body, just one line. You return this. That's the results. Okay. So this is 27. I want to cross check if it is the same. So metric, your height in centimeters will be 170. Yeah, so 170. We use meters. That's why it's 1.7. And then this is 80, right? Okay. Then we compute. You see 27, it's the same. All right. Okay. Now, you can even go on and do this, the categories. So when we calculate, we can check whether it is within this. Then we assign those values and so forth. I think one of the videos I did that. Okay. So this, if I change it, 1.5, and this one is, let's say, 140 kilos. I get 62, right? If you come here, it will tell you that it is what? 62 is obesity, right? Yeah, and so forth. So we can do all this in now by copying this and also putting it in the function. But here, if you want, you can also say tab. Okay, then you bring in the weight, height, and then your BMI. Okay. So it means that I want now a vector okay, which shows me all the, and then I can put names on it, tab, right? And then you have C, you have weight, height, BMI. So that when it comes out, it is no more just, okay, so now I can rerun it. I do the same thing. You see, the weight is this, height is that one. You can even go back and round this one to round to, let's say, 2 decimal places. Because it's 2. So you do that again and run it 2 decimal places. So the weight is this. I will, and then the video, then we can upload it. Okay. So the weight is there, the height is there, the BMI. Okay. So I can do it for 2 people. So one is 1.70, 1.5. Then I do that, and then weight. Oh, that one not. It needs to be a data frame. So it means here I'll have to do data dot frame. That's what you should do, so that it's, and then I need to take this one off and rerun it. So now I can get 2 people, their weights. So this one is 80, this one is 130, like that. So the first person is 1.7, weight 80, and so forth. Yeah, so you do it like that. So if we have even 10, you can have all of them. Okay, so I mean, when you go back, what you can do is that you can also use if or the air supply statement to do this. In other words, if your BMI is less than 18.5, we will say that you are underweight. Okay, we can do so here. How do we? So I can add that. How should I do it? So you have tab. So let's say I call it category. Category. So the category will now be air supply. You take this tab. Okay, so the tab, I can then get a BMI. Because it's a data frame, I take this. Then I go into a function. No, I need to write this outside, otherwise it will be complicated. So BMI.cat is a function. So I'm still writing another function again. What is this function? It takes the value x. If it takes the value x, you must check if x is less than or equal to 18.5. What do? You will say that it is what? Category or classification, whatever you want to call it. Class, let me say class. Its class is what? Where is that one? I need to go down up here. And underweight, right? Okay. So let me put it here. That will be underweight. So you put it there. Next. Okay, so you will say that else, if it is not like that, then it means you must be between 24. But I have already done less than 18. So what I can do is to just write else. No, I have to do else if. Else if so else if you are less than 24, what do we say? You'll be, oh, it shouldn't be 2 like this. So the class will be normal weight. So we copy this and paste it in there. And then we do the next one, else if, okay, so I can copy the whole thing and paste here and change this one to what? Overweight. But if you're overweight, it should be 29.9. And then otherwise, so the other one will be else. Else, we should say you are what? Obese. Okay, so obesity. Okay, so this is a function. It means that this function, you remember that it must have some return. Okay, so return, what are you returning? You are returning the class of the person. Okay, so now let's see. BMI category. Okay, so there it is. We did not have any. So let me take a BMI. We got 62, right? 62.2. It says the person is obesity, right? Okay. Let's put in 12. It will say underweight. So it works. Okay. So it means that I can now go and put this inside my function, and then I will now have the BMI in this category. So that's how you do. So once you know how to write functions in now, you can do anything you want to do. Anything. So I can come back here and say that if you take this, apply the BMI category. BMI cat. Okay. All right. Now, okay, so it should be the other way around. After that, I can now construct my data frame. So this will just be the BMI and not that. Okay, then I can add here, what do they call it in the online? BMI category. Okay. So I can now say that BMI category like this is equal to, what was the name? It's category. Okay. So now I think we are good to go. Let me see if this will work. Error in math list. Non-numeric. Okay, what to be the, okay, so I can rerun it as this with, let me do this and see what is the problem. Okay, so I want to run it here. So I calculate my BMI. I calculate this, it worked. So let's see, BMI is this, and then the category, yeah, overweight, and then we do this, the tab, it worked. I think it's a problem with the round when we want to, good, okay, so I've got it now. So, what do I need to round it before, okay, so, yeah, I need to round this one here. I want to round it, but it's like you are rounding a string. You category obesity, and you say you should round it to 2 decimal places. So it can be. That's the problem. So you see how when you get an error, you have to track back and see how, which means your function, you go in and run it one after the other to see where the problem is. And then, so now it should work. It should work now. Yeah. There it is. So what we saw online is the same thing we have done. So we can also do this as a script, like an HTML, like what they have, and also publish it as well. So that's how it is. So the function actually, you see, we've written two functions using the same principle. That it has a name, it has a function, it has the body is there. You do your computations, you return something. Okay. So this is the BMI to calculate the BMI. But I also wrote another function which will calculate what? The category of the BMI. And then I call one within the other. Yeah, so that's how you write functions. So
I also saw that you did something on pie charts, but then you created your own vector, right? You created your own vector, and then before you did the pie charts, you
Yeah.
said we have to do it in a table form first.
yeah.
I didn't really get that one.
So let's see. Okay, so the data you read, where is it? It's not. I think it's environment. That data, the raw data, I can also read it. Let me see. Let's assume I read everything. Is it? We did this one here today. So when, let me say this is a raw, so raw, it couldn't because there are some problems in there. Okay, but I can use other, what data can I, okay, so there's this data on an array here. Okay, so you see the treatment or even survey. There's a function survey, good. Okay, so survey is a whole lot, 237 statistics students. There are some, so let's say we want a pie chart of the, so what you write, let's say sex, right? Okay, so sex. If I display sex like this, it's so many. I can't put this in a pie chart. Because when you get that, let's say I give this one to you, you have male, female, what do you do you have to get the frequencies. Yeah, so you get the frequencies and then you can now convert it to degrees. And then so it's the same principle. So what I need to do now is just table this. If I table it, I get female number, this number. Okay, so this one, 118, it's not really. So we can also check the pulse. No, pulse is clap 3 levels. Yeah. So this one, you see, so those who clap with the left, neither, right, and so forth. So now you have this. If you have that table, then you can now do a pie chart of it. Yeah. So the raw data you can't do a pie because it's not in frequency form. Yeah. It says tab. Yeah, like that. Okay. So that's how that aspect is. Yeah, but I mean, if you watch what we did, you can get even better. Yeah, by using those Pi 3D charts. Yeah, it's far better. If you are doing some work, then that one is better than the raw Pi chart. Yeah. Is this one for you? The socket. And then this one, take it and give it to Moses. All right. Okay.
I think for now, in Nigeria, with the decisions,
that you have to. Okay. Yeah, but if it is in R, then you can use what we discussed, that the D to get. But other than that, then you need to write the